So our first presenter today will be Tristram Carfrae. It's a pleasure and a privilege to introduce Tristram. He's been responsible for a truly dazzling array of award-winning buildings in his over 39 years with Arup, as a leading structural designer and Arup Fellow and Arup's Deputy Chair. He's also been on the vanguard of something that Graham was talking about just now, designing buildings that consume less resources, less materials and less energy, as well as being quick and keeping an eye on cost. And importantly, also being better environments for us to inhabit every day. So also joining us from London, Tristram, the floor is yours.
Thanks, Bree. Welcome, everybody. I'm delighted you could join us this morning. So I'm going to talk to you about this airport building in Kuwait. It's not a small building. It measures 1.3 kilometres from tip to tip. And the intent of the design was to make a cave, something that protects you from the hot and dusty environment of the Middle East. And we decided that the cave should actually be physically and structurally concrete. So it wasn't just an imitation cave, it was sort of a real cave, although maybe using modern stone rather than ancient stone. The complex curvature of the cave elements is such that no one repeats and each one is different. We do get six-fold repeating because of the symmetry of the three arms, but that's all. And so we came up with an idea of using concrete big beams with pre-stressed ties and then a concrete shell sitting in between the beams, as you can see here. Now, either we could have done this as a conventional 300mm thick in situ shell with a vast complex amount of formwork and a lot of labour, or use modern methods of construction to do industrial manufacturing followed by an assembly process on site. And it won't surprise you to find that we chose the latter. So the shell itself is made up of these panels, roughly 4 meters square. We're using laser cut steel perimeter sides to each panel. This works as permanent formwork and therefore shapes the panel to be exactly what it is that you first thought of. But they also stiffen the panel so that the concrete can be reduced from 300mm thick to 150mm thick and halve the amount of concrete in the whole building. But I think the thing that drove us most was this idea of accuracy, something you can get if things are made directly from a computer. In our case, it had an additional structural advantage in that rather than having large movement joints in roofs that could fill up with dust and sand and stop working over time, we could allow each box to box or intersection to expand and contract very, very slightly by flexing the plate itself. So that if the roof got cold, instead of the concrete cracking, it just flexes the plate boundaries of the box. Here we see the prototype built by the contractor as part just after they won the tender. And you can see the plates being put together, bolted together by these also pre-manufactured cruciform elements. Here you have the concrete not yet placed. And here is the machine that places the concrete. And here you also see digital fabrication at work. Underneath the piece of plastic are a whole array of computer-controlled jacks. These jacks lift and lower automatically for each panel because, as I said earlier, there's no repetition in the geometry, so each panel is actually different. But by having a set of jacks like this, you can see that the bottom formwork can be adjusted between each panel and make mass customization, or each panel is different, but through a manufacturing process. And this is the prototype after it's been concreted up in the air for inspection, so we can see what the soffit quality is like. This is what it looks like on site. The contractor chose to assemble 3x3 9 panels into one piece down at the ground. This piece is then self-supporting and can be lifted up into the air and bolted to the existing roof between supports. We could have made this possibly one panel at a time without supports at all, but the contractor thought he'd reduce his risk by putting in supports every 3 rows of boxes. And here you see the roof coming to shape. You can see that the bolts can take their time going in. This allows everything to settle and make sure it all fits. As I said before, there's not a single piece of on-site adjustment in each shell. You simply make it accurately from an accurate 3D computer model and then bolt it together on site. And here you see a few bays being coming together on site. And when we go inside, you can begin to get the concrete caves I discussed or described at the beginning. It's difficult to tell what it really looks like at the moment because it's still full of the false work supporting every third row of boxes. So that's it from me. Here you can see we didn't intend to set out on a route of digital fabrication. It just seemed to be the natural answer to or solution for the problem that we set ourselves. Thank you very much.